What if I told you that a 50-cent piece of, like, dusty cardboard could cause a $5,000 piece of machinery to literally encase itself in a solid block of ice in the middle of a July heat wave?
I mean, it sounds like a bad prank, right? But in the world of home cooling, it is a very common and very expensive reality.
And that is exactly what we're getting into today. Welcome back to the Deep Dive.
Thanks for having me.
So today we are looking at a comprehensive appliance repair guide out of Bradenton, Florida.
Right, and if you know anything about Florida, you know that a functional air conditioner isn't like a luxury. It is basically a matter of survival.
Totally. But here's the thing. Most of us treat our cooling systems like these magic boxes. We flip a switch on the wall, we hear a hum, and we just expect cold air.
Yeah, and when that doesn't happen, the panic immediately sets in.
Exactly. So today, our mission is to give you, the listener, a highly practical cheat sheet. Whether you're prepping for the summer heat or, you just want to avoid getting scammed by a crazy repair bill.
Which nobody wants.
Right. We're breaking down 5 specific red flags that indicate your air conditioner needs urgent professional repair so you can catch the small stuff before it becomes a complete catastrophic failure. Okay, let's unpack this.
Yeah, to really make use of this guide, we have to completely shift how we think about our home cooling systems.
Okay, how so?
Well, we need to start viewing it as just an appliance that magically produces cold air and start viewing it as this highly complex thermodynamic engine.
An engine.
Yeah, I mean, it is an ecosystem. You've got high voltage electrical components, chemical refrigerants undergoing constant phase changes.
Wow, okay.
Yeah, highly pressurized copper lines and incredibly precise airflow dynamics. All of these elements have to exist in a very delicate, perfectly calibrated balance.
So it's not just a big fan in a box.
Definitely not. When one variable shifts, the entire ecosystem is threatened.
I think that ecosystem framing is really crucial. Like, if we understand the interconnected physics of it, the warning signs make so much more sense. So let's start with the sensory stuff. The things you are going to physically notice in your living space before you ever even think about going outside to stare at the actual machinery.
Right, the immediate environmental changes.
Yeah. The first major red flag is compromised airflow. But the guide makes a really important technical distinction here between air that feels weak and air that feels warm.
Exactly. And, those two symptoms point to entirely different mechanical failures.
Okay, so let's say you put your hand up to the vent, and the air is ice cold, but it's just this, like, sad, weak little puff. What's happening there?
So that means the thermal transfer is working fine, but the physical delivery system is failing.
Gotcha.
That usually points to a failing blower motor that, just can't push the volume. Or, tying back to your opening thought,
The dusty cardboard.
yeah, a severely clogged air filter that is literally suffocating the system's ability to pull air in.
Right. But, okay, what if the air is blowing hard, like plenty of volume, but it's warm? That feels like a completely different beast.
Oh, it is. Looking at the diagnostic tables from the guide, that often points to a failure out at the compressor.
And the compressor is like the heart of the system, right?
Yes.
The thing outside that actually pumps the refrigerant.
Exactly. Or it could be a chemical leak where the system has lost its actual cooling capacity altogether.
And that's stressful. But there's a third airflow scenario that the Bradenton guide highlights, which I just found structurally fascinating.
The attic ductwork issue.
Yeah, like you could have a brand new, top-of-the-line, ultra-efficient compressor working perfectly.
Right.
The blower is pushing massive volumes of freezing cold air. But you have a breach in your ductwork up in the attic. All that beautifully conditioned, really expensive cold air is just leaking out.
Just dumping right into a sweltering, uninsulated space before it ever even reaches your living room.
Which is structurally absurd when you think about it.
Yeah.
You're basically paying a premium utility rate to air condition the underside of your roof shingles while you sit in the living room sweating.
It's the ultimate waste of energy, honestly. And, when that airflow isn't moving properly into your living space, it immediately triggers a secondary problem.
Oh, right.
Which
Yeah.
brings us to the next massive red flag. And this is one you will feel on your skin before you even check the thermostat.
The humidity.
Yes.
This is when you have the thermostat set to, like, a perfectly reasonable 68 degrees, but you're sitting on the couch and the air just feels heavy.
Oh, yeah, sticky.
Your skin is sticky. The house just feels damp and oppressive. I was reading through the mechanics of this and it really clicked for me. An air conditioner doesn't actually make cold air, does it?
Not exactly, no. It removes heat. And in the process of removing heat, it acts as this massive dehumidifier.
Like a giant sponge.
Exactly. What's fascinating here is the physics of that thermal transfer.
Break that down for us.
Sure. So the indoor unit contains an evaporator coil, and that coil is filled with very cold refrigerant. As the warm, humid air from your house blows over that freezing metal coil, two things happen. First, the heat is absorbed by the refrigerant.
Yeah.
Second, because cold air just cannot hold as much moisture as warm air, the water vapor in your home's air reaches its dew point.
It condenses.
Yeah, it condenses into liquid water right there on the coil itself.
So it's exactly like a glass of ice water sweating on a hot patio table.
That is the exact same thermodynamic principle. So a healthy AC is basically constantly wringing the air out like a sponge.
Right.
And in extreme climates like Bradenton, that dehumidification is arguably more important for human comfort than the actual temperature drop.
Because it's just so muggy down there.
Exactly. If the system is running but your house feels like a sauna, it is a glaring indicator that the indoor coil isn't getting cold enough to reach that dew point.
So the equipment is burning electricity, but the physical thermal transfer is completely failing.
Spot on. And when a system is struggling to move air and, failing to remove moisture, the internal components have to work much, much harder to compensate.
Which means things start wearing out.
Yeah.
And you can literally hear it happening, which is our third red flag.
The noises.
Yeah, the normal, comforting hum of the AC turns into something terrifying. We're talking about squealing, loud banging, or like metal-on-metal grinding.
And those sounds are not just annoying. I mean, they are the audible symptoms of active mechanical destruction.
Active destruction, wow.
Yeah, the diagnostic table is very specific about this. Different noises point to different specific failures, but a loud grinding noise, that is universally recognized as failing fan motor bearings.
And bearings are just those little metal balls that sit inside the motor to reduce friction, right? So the fan can spin smoothly.
Correct. Over time, the lubrication breaks down, or grit gets inside them.
Okay.
And when the bearings fail, you lose that smooth rotation. You suddenly have immense friction.
So that grinding sound is literally steel chewing through steel.
It literally is. And the guide classifies this as a medium to high complexity repair. Like, it requires professional intervention to replace the full fan assembly.
You can't just spray some WD-40 on it.
Definitely not. Because if you let that motor keep running while it's grinding, the friction creates immense heat. And that heat will eventually melt the internal wiring of the motor itself.
Oh, wow. Okay, so weak or warm airflow, high humidity, and grinding noises. Those are the sensory warnings, the things that actively disrupt your comfort. But as we move deeper into this guide, it becomes pretty clear that not all failures scream at you.
No, they don't.
Some of the most dangerous warning signs happen completely quietly in the background.
Yeah, the invisible red flags. These are the ones that don't show up in your living room. They show up on your monthly bank statement.
Exactly. The fourth major red flag is a sudden, unexplained spike in your energy bills.
Which is the worst surprise.
It is. Like, if your daily habits haven't changed, you haven't hosted a massive party, and the outside temperature hasn't drastically shifted.
Yeah.
But your utility bill suddenly shoots up 30 or 40%.
Your system is waving a massive white flag.
Yeah. I was thinking about this in terms of your ecosystem analogy. It's basically mechanical compensation, right? Like driving a car with two flat tires.
Oh, that's a brilliant way to conceptualize it.
Yeah. Like if the parts are dragging, the engine has to guzzle twice as much gas just to maintain a normal highway speed.
That's exactly it. The system is programmed to satisfy the thermostat setting you gave it. I mean, it doesn't know it's broken.
Right. It just wants to get to 68 degrees.
Right. So if a belt is slipping or a refrigerant charge is slightly low or, those fan bearings we just talked about are dragging, the physical output drops.
Okay.
So to produce the same amount of cooling you're used to, the machine just runs longer, and it draws significantly more electrical amperage to overcome its own mechanical deficiencies.
So you are paying a massive premium for a system that is quietly tearing itself apart.
Exactly.
Which perfectly sets up the fifth red flag. And I have to admit, when I first read the guide, the physics of this one totally tripped me up.
Short cycling.
Yeah, a phenomenon called short cycling.
Ah, yes. This is a really crucial one to understand.
So, just for everyone listening, short cycling is when the equipment constantly turns itself on, runs for maybe 2 minutes, shuts off, and then turns right back on a few minutes later.
Over and over again.
Over and over. Now, intuitively, I looked at that and thought, wait a minute. If the machine is shutting itself down constantly and spending way more time in the off position than it normally would, shouldn't that use less energy?
Right.
Like, why is this a problem?
Well, it is a very logical assumption, but it completely ignores the electrical reality of heavy machinery.
Okay, tell me why.
The most energy-intensive, stressful, and violent moment for any large mechanical system is the startup phase.
Oh, because it takes so much juice to get all that heavy metal moving from a dead stop.
Precisely. It's called the inrush current. To overcome the physical inertia of the heavy compressor and the fan blades, the system demands a massive, instantaneous surge of electricity.
How massive?
Sometimes up to 3 times its normal running current.
Whoa.
Yeah. But once the components are spinning, the electrical draw drops down and settles into a much lower, highly efficient, smooth power draw.
Okay, so if the system is running for long, smooth cycles, it's highly efficient.
Exactly.
But if it's short cycling, it's essentially enduring that massive, violent electrical surge over and over and over again.
Yep.
Like the difference between cruising cleanly on an open highway versus stop and go bumper-to-bumper traffic where you are constantly slamming on the gas and then slamming on the brakes.
That is exactly it. And that constant surging creates intense heat inside the electrical component.
Which is bad.
Very bad. It burns out the contactors, which are the heavy-duty relays that actually switch the massive voltage on and off, and it radically shortens the lifespan of the motors.
So what actually causes the system to start behaving like this in the first place? Like, why does it get confused?
The guide classifies short cycling as a medium complexity issue because it usually points to a failure in the system's brain.
The brain being the thermostat.
Often, yes. A faulty thermostat that is misreading the ambient room temperature or a failing main control board. The sensors are confused, so they're sending these erratic on and off signals.
Got it.
It requires professional recalibration or a board replacement to get the ecosystem back in sync.
Okay, so we've mapped out our 5 red flags. We've got airflow issues, high humidity, strange noises, spiking energy bills, and short cycling.
Right.
But here is the reality of being a homeowner. Calling a repair technician feels like a hassle.
Oh, it's a huge hassle.
It's expensive. You have
Yeah.
to take time off work. So, a lot of people will just turn up the TV to drown out the grinding noise, or they'll ignore the high bill and just hope the machine survives the summer.
Which is a huge gamble.
Right. So if you ignore these signs, how quickly do things actually spiral?
Because of the deeply interconnected nature of this ecosystem, they spiral incredibly fast. The guy actually has a fascinating FAQ section that addresses this exact homeowner complacency.
Let's hear it.
Let's revisit that 50-cent air filter from your introduction.
Yes. People are always told to change their filters, but it usually feels like arbitrary advice. Like, how does a piece of dusty cardboard take down the entire ship?
It happens through a ruthless thermodynamic chain reaction.
Okay.
As we established, the indoor coil needs a constant flow of warm air from your house to absorb heat.
Right, to work like a sponge.
Exactly. Let's say your filter is completely caked in dust and pet hair. It deeply restricts that warm airflow.
So the freezing cold refrigerant is pumping into the coil,
Yeah.
but there's no heat to absorb.
Right. And refrigerant enters that coil at sub-freezing temperatures. It absolutely needs the heat from your home's air to boil from a liquid into a gas.
Oh, I see.
If that warm airflow is choked off, the temperature of the physical copper coil drops below freezing. Yeah. The ambient moisture in the air, that humidity we talked about earlier, condenses on the coil and instantly turns to ice.
Wow.
Within hours, it becomes a solid block of ice, completely suffocating the system.
And the machine just keeps running while it's frozen solid?
This is where it gets really dangerous. The thermostat still reads that the house is hot, so it keeps demanding cold air.
Because no air is getting through the ice.
Exactly. It forces the outdoor compressor to keep frantically pumping refrigerant. But because the indoor coil is frozen, the liquid refrigerant never boils into a gas.
Wait, so it stays a liquid?
Yes. It travels back to the compressor as a liquid. This is called slugging.
Slugging.
Compressors are designed to compress gas, not liquid.
Oh, man.
Trying to compress a liquid physically destroys the internal valves of the compressor. It overheats, and if you're lucky, an automatic safety switch shuts it down.
And if you aren't lucky?
It literally tears itself apart. All of that just from a dirty filter.
That is incredible. A totally catastrophic failure born from the smallest possible maintenance oversight.
Yep.
And the guide points out another specific, highly common mechanical failure that creates a similar domino effect. Here's where it gets really interesting. The capacitor trap.
Ah, yes.
Let's imagine you are standing outside and you hear your outdoor unit humming really loudly. It sounds like electrical power is flowing, but you look through the metal grate, and the big fan blades on top are not spinning at all.
Just sitting there.
Yeah. The guide states that is likely a dead capacitor.
Yes. A capacitor is a small, relatively inexpensive cylindrical component that sits near the circuit board. You can think of it as a specialized battery that stores a massive, instantaneous jolt of electricity.
Like the starter motor in a car.
Right.
You turn the key, the battery gives the starter that huge initial kick of amps to get the heavy engine parts moving.
A very apt comparison. We talked about that massive inrush current needed during startup. The capacitor provides that. It gives the fan motor and the compressor the massive electrical kick they need to overcome physical inertia. But capacitors are incredibly sensitive to heat, and over time, the dielectric fluid inside them degrades.
Okay, so when they die, what happens?
If the capacitor dies, the system calls for cooling. The main power arrives, hence the loud humming you hear. But the motor doesn't get that initial kick, so the fan can't physically start turning.
And if you don't know any better, and you just let it sit there humming,
Yeah.
then you are falling right into the trap.
Yeah.
The outdoor fan's entire job is to exhaust the massive amount of heat that the compressor is generating.
Right.
If the fan isn't spinning, all that heat is trapped inside the metal box. The compressor will rapidly overheat.
Oh, no.
Ignoring a simple, cheap, low-complexity part like a capacitor forces the absolute most expensive component in the entire system, the compressor,
Yeah.
to literally cook itself to death.
Wow.
You've just turned a quick, inexpensive part swap into a total system replacement.
It's terrifying how fragile the whole setup actually is. It really is. And the ripple effect goes even further than just the air conditioner itself. We have to look at the whole house ecosystem.
The whole house.
Yeah. When a compressor is struggling to start or overheating, it does not draw power smoothly from your home's electrical panel. It causes massive erratic power surges.
Which affects everything else plugged into the walls.
Exactly. Those unpredictable electrical spikes travel backward through your home's wiring. They can easily overwhelm surge protectors and permanently fry the delicate circuit boards in your smart TVs, your computers, or your gaming consoles.
Wait, really? So a failing AC capacitor could literally fry my laptop?
Potentially, yes. Furthermore, consider the ambient heat. If your cooling system goes down in a place like Bradenton, the temperature inside the house climbs into the upper 80s or 90s incredibly fast.
Yeah, within hours.
That forces every other appliance in your home to work significantly harder. Your kitchen refrigerator, for instance, is calibrated to operate in a 72-degree room. Suddenly, its own compressor has to fight against an 85-degree ambient temperature just to keep your milk from spoiling.
Wow. So on top of a massive HVAC repair bill and, potentially replacing your computer, you are risking hundreds of dollars in grocery spoilage because the refrigerator's compressor burns out trying to compensate for the AC breaking.
Exactly. Everything is connected.
Everything is connected. The stakes are just so much higher than just feeling a bit warm for an afternoon.
Much higher.
Well, let's pivot to the most visceral, panic-inducing symptom mentioned in the entire guide. The one failure that will make any homeowner immediately sprint to the phone.
The indoor water emergency.
Yes, the water leak.
This is when the failure breaches the boundary of the machine and begins actively destroying your home's architecture.
It's the worst.
When you see water pooling around your baseboards, soaking into your carpets, or dripping through the ceiling drywall beneath your attic unit, immediate triage is absolutely necessary.
So what's step one?
The very first thing you must do not wait for a technician, is go to the thermostat and turn the system completely off.
Cut the power.
Cut the power immediately to stop the flow of condensation and prevent severe structural rot to your framing and drywall.
Okay, system off, power cut. But mechanically, how is an air conditioner producing enough liquid water to actually flood a living room? Like, where is it coming from?
This goes back to the dehumidification principle we discussed earlier. In a humid climate like Florida, a standard residential AC unit is pulling an astonishing volume of moisture out of the air, sometimes up to 20 gallons of liquid water every single day.
Wait, 20 gallons?
Yeah.
That is basically an entire bathtub's worth of water being pulled out of thin air every single day inside your house.
Precisely. And all of that water drips off the freezing coils into a shallow metal drain pan, and it relies on a tiny, typically 3/4-inch PVC pipe to drain harmlessly outside.
That's a tiny pipe for 20 gallons.
It is. But over time, that dark, damp PVC line becomes the absolute perfect breeding ground for algae and mold.
Because it's dark, it's wet, and it's constantly fed by the dust and organic matter bypassing the filter.
Exactly. The algae grows thick, creates a physical gelatinous blockage in the pipe, and the water simply backs up.
Yikes.
With nowhere to go, 20 gallons of water overflows the rusted drain pan directly into your house.
Okay, so it's a plumbing clog. I've seen tons of DIY videos online where people say you can just fix this by pouring some hot water and white vinegar down the access pipe to kill the algae.
Oh, I've seen those too.
So why is the Bradenton guide so incredibly adamant about professional intervention for a clogged pipe?
Yeah.
Like, why does the DIY route fail?
Because professional diagnostics aren't just about clearing a single immediate symptom. Pouring vinegar might kill the surface algae and get the water flowing today, but it doesn't address the holistic health of the ecosystem.
I see.
When a professional technician arrives, they perform a comprehensive, multi-point inspection. They don't just snake the drain line.
What else are they looking for?
They evaluate the condition of the drain pan itself, which, might be rusted through and need replacement.
Right.
They test those electrical contactors we talked about, the heavy-duty voltage switches, to ensure the violent startup sequences are operating within safe parameters.
Okay.
They hook up specialized gauges to pressure test the chemical refrigerant levels to ensure you don't have a microleak. And they use commercial-grade algicides to properly sanitize the drainage area, guaranteeing the blockage won't return next month.
So they're really doing a full
Yep.
workup.
They are diagnosing the ecosystem, not just treating a symptom.
It makes sense. It's the difference between taking an over-the-counter painkiller for a severe toothache and actually going to the dentist to have the cavity properly drilled and filled.
Exactly.
The DIY approach just masks the deeper rot.
If we connect this to the bigger picture, you really have to factor in the environmental demands. In extreme, unforgiving climates like Bradenton, Florida, the intense heat and heavy humidity dictate that these residential units are running almost year-round. They never get a break.
They simply don't get an off-season break. The mechanical wear and tear is relentless. That is why the guide is so insistent that biannual professional inspections are vital.
It's preventative care.
It's the only way to extend the equipment's lifespan and avoid these catastrophic domino effects.
It's not an optional luxury. It is strictly required maintenance for existing in that climate.
Truly.
So let's do a quick recap for everyone listening so you have this cheat sheet ready. The 5 red flags you need to watch out for. Number 1, compromised airflow. Weak air means a fan or filter issue. Warm air means a compressor or refrigerant failure.
Right.
Number 2, high humidity. Your house feels sticky because the coils aren't getting cold enough to condense the water vapor.
Yep.
Number 3, strange noises. Metal grinding means your bearings are actively chewing themselves to pieces.
Number 4, spiking energy bills. Your system is mechanically dragging and burning excess electricity to compensate. And number 5, frequent cycling. The system's brain is confused, forcing the motors to endure endless, violent electrical surges.
That's the list.
So what does this all mean? It means you have to be highly proactive. Waiting for the system to completely die before calling a professional is mathematically the most expensive possible way to manage your home.
Without a doubt.
Paying attention to these subtle early warnings is the only way to protect your physical comfort, the structural integrity of your home, and your bank account.
I couldn't agree more. And, examining the sheer fragility of all this, how a single clogged filter or a tiny degraded capacitor can cause massive electrical surges, threaten your refrigerator, and risk flooding your drywall with 20 gallons of water, it actually raises a much larger, frankly concerning question about how we live today.
Oh, I can hear the wheels turning. What are you thinking?
Well, this entire conversation highlights a massive vulnerability. As global temperatures continue to rise and more regions begin experiencing the kind of extreme year-round heat and humidity that places like Bradenton have always dealt with, it makes you seriously question our modern residential infrastructure.
I mean, how we design houses.
Exactly.
Yeah.
Are our modern homes too precariously dependent on a single, highly complex, surprisingly fragile outdoor compressor just to remain habitable?
That is a fascinating point.
We have engineered these incredibly tight, sealed boxes to live in, but the entire household ecosystem essentially collapses if one single fan bearing fails or a PVC pipe gets a little bit of algae.
Right, the whole house goes down.
It strongly suggests that future residential architecture might need to fundamentally shift its focus. We need to lean much more heavily into passive cooling, utilizing smart shading, strategic airflow cross-ventilation, and thermal mass materials that naturally regulate temperature.
Just to take the pressure off the machines.
Right. We simply shouldn't be entirely at the mercy of one spinning motor and a chemical phase change just to ensure our living rooms are safe to sit in.
Wow. That is a massive paradigm shift. From diagnosing a squeaky fan motor to fundamentally rethinking how we build human shelter altogether.
It's all connected.
That is definitely something to chew on the next time you hear that outdoor unit violently surge to life outside your window. We want to thank you so much for joining us on this deep dive. Stay vigilant, stay cool out there, and we'll get you on the next one.